kind of is. This machine is essentially a giant racetrack, but instead of cars, it smashes subatomic particles together at nearly the speed of light. Pretty mind-blowing, right? Think of it this way, the LHC is like a time machine, allowing us to see what the universe might have been like just after the Big Bang. It's a marvel of engineering, a massive ring stretching 17 miles wide and buried a whopping 175 meters underground. And it's not just in one country, it's built in collaboration between France and Switzerland, displaying international teamwork in the pursuit of scientific discovery. This scientific powerhouse comes with a hefty price tag, though. The LHC cost a cool $4.5 billion to build and even more to maintain and upgrade. But the payoff has been significant, helping us unlock secrets of the universe at its most fundamental level. So, how does this wonder machine work? It's all about velocity. The LHC whips subatomic particles around its track until they are practically flying at the speed of light, making thousands of laps per second. How do they achieve such incredible speeds? With the help of incredibly powerful electromagnets, generating a magnetic field thousands of times stronger than Earth's own. Some folks were understandably worried about the impact of such a strong field on nearby electronics and even the planet's magnetic balance. But that's just the setup. Once these particles reach their top speed, nearly 1 million times faster than sound, they smash into each other head-on. That's what the LHC is designed to do, and it's this collision that scientists are truly interested in. It's through these collisions that we hope to learn more about the fundamental building blocks of our universe. The crash between these particles is no joke. It unleashes a huge burst of energy, spawning a whole bunch of different subatomic particles. These new particles scatter in all directions, but they're like fireworks, here 1 minute, gone the next. Most of them disappear almost instantly. Fascinatingly, by changing up the types of particles they smash together, scientists can potentially discover entirely new particles hiding within the mayhem of the collision. To capture these fleeting moments, they've built incredibly sensitive detectors around the collision points. Think of these detectors as superpowered cameras recording every detail of the crash. The only problem? All this action creates
is shutting down for almost 4 years, but few know what this actually means. CERN is best known for identifying the God particle. The facility has been long accused of opening portals to different dimensions and realms. Sound crazy? Then consider this giant statue of Shiva outside the facility, a false Hindu deity associated with the cosmic dance of creation and destruction. And what's even more insane is that in 2016 an occult ritual was called a camera directly in front of the statue. Officially, CERN says that it's shutting down to prepare for the next phases of the Large Hadron Collider, but the public just pointed out a disturbing pattern. Every time CERN enters one of these shutdown cycles, major disasters and disruptive world events seem to take place. The financial crash of 2008, the chaos that was 2020, but here's what most people are missing. Even if the
machine 17 miles around smashes particles together at almost the speed of light. In December, it spat out a result that bent the rulebook scientists had trusted for 50 years. We're going inside the strangest signals ever caught at CERN. A particle that fell apart the wrong way. Matter that beat its evil twin. Antimatter. Trapped and then dropped, just to watch which way it falls. If this blows your mind, hit like and subscribe. Helmets on. We're going down. Picture a circle so big it crosses an international border, and it sits about 100 feet beneath your shoes. That circle is real. It runs under farms, under villages, under the edge of the Alps.
Welcome to Open Your Reality. My name is Chad.
LS.
Harness or accidentally disrupt dark matter, the repercussions could be catastrophic on a cosmic scale. Then there's dark energy, the mysterious force driving the universe's expansion at an accelerating rate. Could CERN's research have revealed a method to manipulate this force and...
So CERN is set to close down on June 29th, 2026. Okay?
Again.
It'll be shut down for 4 years until June of 2030. So that's fun, you know, especially given that they're building a new one, which is like 10 times the size of the current one, something like that.
Are they really?
Yeah.
Where?
I'll show you. We'll pull it up in a second. So the last time it shut down was between 2018 and 2022.
That was a fun time for us all, wasn't it?
Listen, I didn't think that there was any like unrest around the world at all, right? There's zero doubt that between now and 2030, the entire world will be radically changed. That's for absolute sure.
I have goosebumps.
And this is all happening as AI emerges as this thing that is going to literally completely change the whole world. You got to ask yourself, doesn't it feel like that all kind of came out of nowhere? You know what I mean? You're like, I mean, I know they've been talking about AI, whatever.
Oh
but
yeah,
it's
it
like,
just like popped up one day and it's like, oh, ChatGPT's here.
and
There you go.
Especially if you've heard the old rumor that this machine would create a black hole and destroy Earth. Wait, is it finally happening? Is that why they're shutting it down? So, the Large Hadron Collider, or just the LHC, is the biggest science machine ever built. It's a giant ring-shaped tunnel deep underground near Geneva, where scientists smash tiny particles together at crazy speeds. They do it to copy, for a split second, what the universe was like right after the Big Bang. By recreating those conditions, the experiment could reveal some of the universe's deepest secrets. And now, this iconic machine is shutting down. It won't be permanent though. They have to power it down so the team can do major engineering work and install some big upgrades. And that process will take around 5 years. Scientists guarantee the LHC isn't shutting down because of a problem. If anything, the machine is still working great and gathering massive amounts of data. But don't get it twisted. The famous atom smasher isn't going to run forever. It will probably retire around 2041. And after that, it may be replaced by a massive machine called the Future Circular Collider, or FCC. But before we explain what's coming next, let's talk about how the Large Hadron Collider actually works. This is the world's most powerful particle accelerator. Think of it as a metal ring buried deep underground right under the border between France and Switzerland. And it's huge, around 17 miles around. It was built to answer a very old question. What is everything made of? Basically, the LHC lets scientists recreate conditions similar to those right after the universe began. Inside this ring, scientists send tiny particles racing around at almost the speed of light. These particles are like microscopic race cars, guided by powerful magnets that bend and steer them around the loop again and again. As they go faster and faster, they carry enormous energy, even though they're unbelievably small. At certain points around the ring, scientists smash these particles together head-on. When they collide, they break apart and turn into showers of other particles. Scientists record everything they can about those conditions, and basically hope it helps answer some huge questions about the origin and structure of reality itself. This $10 billion project began in 1989 and became operational in 2008. Then, in 2012, it made a major breakthrough by discovering the Higgs boson. This is a fundamental particle associated with the Higgs field, a theory first proposed back in the 1960s. To understand it, let's use a rock and a light. Both are
Apparently they're turning CERN off in July. We've been told it's maintenance. That's the reason why they're turning it off. So we thought we'd look into CERN again.
Technologies we develop here at CERN, they do change. Okay, I know what you're probably thinking. The Large Hadron Collider is shutting down, and that's supposed to be great news? How does that even work? Well, it might sound completely backwards, but believe me, what's about to happen is genuinely one of the most exciting stories in all of science right now. So, just imagine this. The most complex, most powerful machine humanity has ever conceived of is about to get switched off. And not just for a little while. We're talking 4 years. Yeah, on the surface, that sounds like a total disaster for science, right? But it's not. In fact, it's the complete opposite. This shutdown is exactly what we need to push physics into a brand new era. This isn't about stopping, it's about transforming. All right, so let's get into it. This is a planned shutdown, a transformation, not a pause. And the first thing you have to know is that this is not some kind of emergency. Nothing's broken. This is a huge, incredibly ambitious project that has been in the works for years. Okay, so here are the specifics. The official name is Long Shutdown 3. It all starts in June of 2026, and it's gonna last for about 4 years. During that time, teams of brilliant physicists and engineers from all over the world are going to descend on this thing and basically perform a massive overhaul. The goal isn't just a tune-up, it is a total metamorphosis. So, before we get into the upgrade itself, let's take a quick step back. What even is the Large Hadron Collider? Because, to really understand why this change is such a big deal, you gotta appreciate the absolutely mind-blowing machine we already have. Think of it like this. The LHC is a giant, 27-kilometer underground racetrack buried deep beneath the border of Switzerland and France. Scientists take tiny particles, protons, and whip them around this ring until they're traveling at, get this, 99.9999991% the speed of light. I mean, just absurdly fast. Then they steer them into a head-on collision. For just a fraction of a second, that smash creates a tiny fireball of energy that mimics the conditions right after the Big Bang. It's like a time machine to the dawn of the universe. And you know what? This wild idea absolutely works. Back in 2012, the LHC had its biggest celebrity moment when it discovered the Higgs boson. This was a huge deal. It was the last missing piece of our main theory of reality, the standard model of particle physics. The Higgs is the particle that gives everything else mass. Finding it was a monumental triumph. So, if it's so great, why mess with it? Well, because to answer the next round of big questions, we have to turn the dial way, way up. We need 10 times more collisions. That is exactly what this high luminosity upgrade is all about. Now, the key word here is luminosity. It sounds complicated, but the idea is actually pretty simple. In this world, luminosity is just a measure of how many collisions you can generate every second. So more luminosity means more particles are smashing together. And crucially, the more things you smash together, the better your odds are of seeing something incredibly rare. And the scale of this leap is just staggering. The new machine isn't going to be a little bit better, it's going to be 10 times more luminous. This isn't a small tweak, it's a colossal jump in power. For every one collision event we can create today, the high luminosity LHC will create 10. It's a whole new ballgame. And that's really the whole point here. More collisions isn't just about filling up hard drives with more data, it's about better science. It's about increasing our chances dramatically of catching a glimpse of something totally new, something that's been hiding from us just because it almost never happens. Think about the advantage this gives us. We're going from the realm of billions of collisions to the realm of trillions. And that huge jump means we can go from maybe just glimpsing a super rare event to actually being able to study it. Before, you might see a weird blip in the data and just have to shrug. But now you can see that blip over and over again and confirm it's real. That's how you go from just testing the theories you already have to discovering completely new physics. And at the end of the day, that is the ultimate prize. This entire 4-year, multi-billion-dollar project is about one thing: hunting for answers to the biggest, most fundamental questions we have about reality itself. For starters, what is dark matter? We know it's out there. We can see its gravity holding entire galaxies together like some kind of invisible cosmic web. It makes up about 27% of the known universe, and yet we have absolutely no clue what it is. With 10 times the collisions, we might finally have a chance to produce a dark matter particle and get our first look at this hidden universe. Or how about this one? Why are we even here? Our theories say the Big Bang should have created equal amounts of matter and antimatter. If that happened, they would have instantly wiped each other out, leaving behind a universe with nothing but light. The very fact that you and I and everything we see exists means something's a bit off. There has to be a tiny difference between matter and antimatter, and the new LHC might just be powerful enough to finally spot it. And then we get into the really wild stuff. The ideas that sound like pure science fiction. Could there be hidden dimensions? Some of our best theories actually predict extra dimensions of space. They're just curled up so tiny we can't perceive them. The colossal energy of the new LHC might just be enough to knock on the door of one of these dimensions, even for a split second, and reveal a much stranger reality than we ever dreamed of. So all of these huge, profound questions point to one single conclusion. Our current best theory of everything, the Standard Model, is a masterpiece. It works incredibly well, but we know it's incomplete. It has these giant holes in it. It can't explain dark matter or the matter-antimatter mystery. It doesn't even include gravity. We know there's a bigger story out there, and this upgrade is designed to go find the next chapter.
So when we look beyond this 4-year shutdown, what we're really seeing is the stage being set for a new golden age of discovery.
And you know, this isn't the first time this has happened. The LHC went offline for an upgrade back in 2013 and again in 2018. It's part of the machine's planned life cycle. Each time it came back more powerful than before, but make no mistake, Long Shutdown 3 is the big one. This is by far the most ambitious leap yet.
So, circle the year 2030 on your calendar. That's about when the newly christened High Luminosity LHC is expected to power back on. And when it does, it's going to unleash an absolute fire hose of data unlike anything physicists have ever had to deal with before.
And that's why this is so important. With this unprecedented flood of information, scientists can measure things we already know, like the Higgs boson, with an exquisite, almost unbelievable precision. They'll be looking for the tiniest deviation from what our theories predict, because that tiny wobble could be the first hint of new forces or particles. This is one of humanity's best shots at finding physics beyond the Standard Model.
So in the end, the LHC isn't being retired. It's not broken. It's going into a chrysalis so it can emerge as something far more capable. A machine ready to tackle mysteries that were completely beyond our reach before.
And that leaves us with the most exciting question of all. With the power to see things that are 10 times rarer than ever before, what's been hiding just out of sight? What new truths about our universe are waiting to be found in those trillions of collisions? The search begins around 2030.
Meters of solid rock, a machine is doing something no civilization before ours has ever managed. It is breaking matter open at the most fundamental level physics will allow. The Large Hadron Collider drives twin beams of protons around a 27-kilometer ring at 99.9% of the speed of light. The collisions that follow reach temperatures approaching 10 trillion degrees, and the data coming back from those collisions is quietly dismantling a framework that physicists have trusted for half a century. Tonight we are going inside that machine. We will cover the particles that refuse to behave, the hidden layer of reality too small for any instrument alive to reach, the invisible majority of the universe that physics cannot explain, and a calculation about the ground state of the universe itself that some physicists genuinely struggle to say out loud. This one goes deep. If this kind of content does something to you, subscribe now, because what we are about to cover changes how you see everything. Here is everything you need to know. Somewhere beneath the rolling farmland that straddles the border of France and Switzerland, sealed away from every noise and vibration on the surface, sits the most powerful instrument the human species has ever assembled. You would never know it was there. A few low industrial buildings scattered across the landscape, some ventilation ducts rising out of the grass at irregular intervals, power lines cutting across the horizon toward the facility. Nothing about the surface gives the machine away. There are no signs, no dramatic architecture, no indication whatsoever that something world-altering is happening below your feet. What the machine is doing underground is this. It is recreating conditions that have not existed since the universe was less than a heartbeat old. Scientists are driving protons together with enough force that the collision point briefly becomes one of the hottest places in the known cosmos. Not the hottest place near Earth, not the hottest place in the solar system. One of the hottest places anywhere in the observable universe, recreated deliberately under controlled conditions, inside a tunnel buried beneath farmland in a landlocked region of Western Europe. That collision point, a region smaller than a single atomic nucleus, touches temperatures that existed only in the first fraction of a second after everything began, before stars, before galaxies, before atoms themselves had any right to exist. The machine is called the Large Hadron Collider. Its tunnel runs in a circle measuring just over 27 kilometers in circumference. If you drove that loop on an open road at highway speed, it would take you roughly 20 minutes. That is not a particularly large circle by any ordinary measure. But inside that tunnel, sealed inside pipes thinner than a human arm, proton beams complete that same circuit 11,000 times every single second. Not 11 times, not 1,100 times. 11,000 complete circuits every second. If you blink, the protons have completed roughly 15,000 laps before your eyelid opens again. At any given moment, the two beams together contain hundreds of billions of protons, and every one of them is racing in opposite directions around the ring at a speed so close to the speed of light that the difference between their velocity and the absolute speed limit of the universe is less than 4 meters per second. The magnets that hold those beams on course are cooled to minus 271 degrees Celsius. That is colder than the surface of Pluto, which already sits so far from the Sun that sunlight there is roughly 1,600 times dimmer than it is on Earth. It is colder than the background temperature of deep space, which itself sits just a few degrees above absolute zero. The engineers who built this machine had to construct the largest ultra-cold object on Earth, just to keep the protons aimed correctly around the ring. Nothing in the natural environment near our planet is this cold. This coldness had to be engineered from scratch and maintained continuously, year after year, by cryogenic systems running without pause. The project took decades of design and construction before the first beam circulated. Scientists from more than 100 countries contributed components, calculations, and expertise to it. When it first powered up in September 2008, there were people standing outside the facility carrying signs warning that the collisions would generate a microscopic black hole capable of swallowing the Earth from the inside. Tabloid newspapers ran headlines about the end of the world. Philosophers wrote essays about scientific hubris. A handful of legal challenges were filed in multiple jurisdictions attempting to halt the experiment on safety grounds. The physicists checked the mathematics carefully, reviewed every calculation from multiple independent angles, and concluded with high confidence that the scenario being described was physically impossible. They switched it on regardless. The Earth survived. But something else began that day. Something quieter and, in certain ways, more genuinely unsettling than any black hole. The machine started producing numbers that did not match the predictions, not dramatic failures, not readings that were completely off the scale, small deviations, fractions that looked like rounding errors at first glance, except that they kept reappearing in independent experiments run by separate teams using separate instruments at separate points around the ring. The rulebook that had governed particle physics for 50 years began showing signs of strain, not in one place, in several places simultaneously, and the more carefully scientists looked, the more signs they found. The machine did not end the world. It may instead be showing us that the world is stranger and deeper than the best physics we have been able to write down. There are roughly 2,700 scientists working on the collider right now, scattered across dozens of countries and hundreds of institutions. A substantial number of them are chasing a version of the same thing.
evidence of a layer of physical reality that sits below anything a human instrument has ever reached. A layer where the current rules may not just bend, but collapse entirely. Where forces that have no names in any textbook and particles that no detector has ever caught might be operating in ways that determine everything about the universe above them. The mass of every particle, the strength of every force, the reason anything exists at all rather than nothing. The search for that layer is what this is about. The machine buried under Europe is the most precise instrument ever constructed by the human species. It draws enough electricity to power a medium-sized city around the clock. Its largest detectors outweigh the Eiffel Tower, and after decades of operation, accumulating data one collision at a time, it is closing in on something that defies every framework physicists have trusted since the middle of the 20th century. What exactly that something is, no one fully agrees on yet. The theoretical models being proposed to explain the anomalies are diverse and sometimes incompatible with each other. But the data itself keeps pointing in a consistent direction, and the researchers who spend their careers staring at that data, the people who know it most intimately, are starting to look genuinely uneasy, not worried, not panicking, something more specific than that. The expression of someone who suspects the thing they have been chasing for decades might actually be there, and is not entirely sure they are ready for what finding it means. For 50 years, a single theoretical document has governed particle physics. Scientists call it the Standard Model. It is a mathematical framework, a precise and interlocking set of equations that describes every particle ever detected in any laboratory anywhere in the world, and accounts for 3 of the 4 fundamental forces that shape the universe at every scale smaller than a galaxy. It covers the electromagnetic force, the force that underlies chemistry, generates light, drives electrical current through every wire ever manufactured, and holds electrons in orbit around atomic nuclei. It covers the strong nuclear force, the force that locks quarks together inside protons and neutrons with an intensity so extreme that it makes the electromagnetic force look trivial by comparison. And it covers the weak nuclear force, the force responsible for certain types of radioactive decay, and for the nuclear reactions that powered the early universe through its first few minutes of existence. 3 forces, dozens of particles, thousands of independent experimental confirmations. It is the most thoroughly tested scientific theory ever produced by the human mind. Experiment after experiment across decades, and across every particle accelerator ever built, has confirmed its predictions to 1 part in a billion. So when physicists say it is beginning to break, that statement does not arrive lightly. The Standard Model was assembled through decades of collaborative work in the middle of the 20th century, built piece by piece from theoretical predictions and experimental confirmations that accumulated across generations of physicists working on both sides of the theoretical and experimental divide. Every particle it predicted was eventually located in an experiment. The electron neutrino, the muon, the gluon, the W and Z bosons, the top quark, each prediction confirmed, one after another, over a span of decades. The final missing piece was called the Higgs boson, the particle tied to the mechanism that gives all other particles their mass. Scientists at the Collider confirmed its existence in 2012, after a search that had lasted nearly 50 years from the moment the particle was first theoretically proposed. The physics community celebrated. Every missing piece accounted for, every prediction confirmed. The framework was complete. Then the questions started, and they have not stopped since. The Standard Model works with extraordinary precision inside its own domain. Inside a laboratory, under controlled conditions, at the scales human instruments can currently probe, the model is essentially perfect. But pull back to the scale of the actual universe, and the failures arrive immediately, and they are not small failures. They are fundamental ones. The model says absolutely nothing about dark matter, the invisible substance that accounts for approximately 85% of all mass in the cosmos. This is not a minor gap. This is the model failing to describe the dominant component of all the matter that exists. It cannot explain dark energy, the force that is causing space itself to expand at an accelerating rate, a phenomenon confirmed by independent observations using multiple different methods. And it cannot answer what many physicists consider the deepest puzzle in all of science. Why does anything exist at all? According to the Standard Model, the Big Bang should have produced matter and antimatter in perfectly equal quantities. Every particle created alongside an antiparticle twin of opposite charge and equal mass. And when matter and antimatter meet, they annihilate each other completely, without remainder, converting entirely into energy. If the equations were correct, the universe should have destroyed itself in the first fraction of a second after it began. Everything cancelling everything else out, nothing left. A cosmos of pure diffuse energy dissolving into an empty vacuum. No stars, no galaxies, no planets, no atoms, no observers. You exist. That is the proof something went differently. The atoms in your body are made of matter. The air you are breathing is made of matter. Every star in every galaxy in the observable universe, every object that has ever been detected by any telescope or instrument pointed at the sky, is made of matter. Antimatter exists in tiny, fleeting amounts, created briefly in particle collisions and in certain radioactive processes, but immediately destroyed upon contact with the matter surrounding it. The universe is overwhelmingly composed of one type, and physics cannot tell you why. Something in the earliest moments of the universe tilted the balance. Matter won by a margin so thin it is almost impossible to express. For every billion antiparticles that existed in the first instant, there were 1,000,000,001 particles of ordinary matter. The billion pairs annihilated each other without trace. That single extra particle in every billion survived. And that fraction, that impossibly thin margin of survival, became every star ever formed, every planet ever assembled, every molecule in every living thing that has ever existed, anywhere in the observable universe. Everything you have ever seen, touched, smelled, tasted, or heard is made from those survivors. But the Standard Model cannot tell you what caused that margin. The answer lies somewhere outside the framework. This is not a new problem. Physicists have understood these gaps for decades. They have built extensions and added auxiliary theories, proposed corrections and modifications, and nothing has sealed the holes cleanly. And recently, something new appeared in the collision data. Particle behaviors that deviate from standard model predictions. Small deviations, barely measurable at current levels of precision, but appearing consistently across multiple independent experiments conducted under different conditions, and doing so in the same direction. Random errors scatter in all directions. Systematic signals point. The data is pointing. And scientists are now seriously discussing the possibility that the Standard Model is not just incomplete, but fundamentally wrong at scales smaller than any instrument has ever reached. That the universe is operating on a deeper set of rules hidden just below the current floor of human detection, where the Standard Model's equations give way to something more fundamental, something that would rewrite every physics textbook in existence and answer questions that have been sitting open for half a century. Finding those rules would represent the largest scientific breakthrough in human history, larger than the discovery of gravity, larger than the theory of relativity, larger than the decoding of the genetic code. And the search for them requires going somewhere no machine has ever managed to reach, to a scale of reality so small that everything you know about the physical world looks enormous by comparison. The morning of July 4th, 2012, began like any other at the facility outside Geneva. By that evening, it had become one of the most significant days in the history of science. In a packed auditorium, with physicists standing in the aisles and crowding the back of the room, a researcher walked to a podium and announced that after nearly 5 decades of searching, the Higgs boson had been found. One of the scientists in the audience began to cry. Another applauded until his hands went numb and red. Peter Higgs himself, the man who had first predicted the particle's existence back in 1964, was seated in the front row. He was 83 years old. He had spent his entire adult life waiting for this moment, reading papers written by other physicists about his prediction, watching experiments at accelerators across the world search for the particle with successively greater energies and successively greater sensitivity, and every time not finding it. Until that morning. The discovery was real. The particle was real. Its properties matched the predictions with remarkable precision. By any measure and from any angle, it was one of the great moments in scientific history, the culmination of 50 years of work by thousands of scientists across dozens of countries. The champagne was opened, the speeches were made, the papers were filed in the scientific journals, and almost immediately the celebration created a new and entirely unexpected problem. The confirmed mass of the Higgs boson came in at approximately 125 giga-electron volts. For most people, that number means very little, but when you feed that specific value into the equations governing the stability of the vacuum of space, what comes back is not reassuring. The number sits in what physicists call the metastable region of the stability phase diagram. Not light enough for the vacuum to be completely and permanently stable. Not heavy enough for the vacuum to be obviously unstable and already in the process of collapsing. Right at the edge between the two. A middle state. A condition that can persist for an enormous length of time, potentially far longer than the current age of the universe, but which is not, strictly speaking, the lowest energy state available to the universe. Picture a ball resting in a shallow depression carved into the side of a long slope. The ball is still. It looks stable. It behaves as though it is going to stay there indefinitely. The depression keeps it in place through ordinary mechanics. But the depression is not at the bottom of the slope. It is partway up. And in the language of quantum mechanics, particles and fields do not actually need to be pushed over barriers in order to cross them. They can tunnel through, not metaphorically, not as an approximation, literally. Quantum tunneling is a real, measured, confirmed phenomenon. Fields that appear stable can spontaneously transition to lower energy states through this mechanism. The probability is very small for any given region of space in any given moment. But given enough time and enough volume of space, a transition that has any non-zero probability eventually happens. The universe may be sitting in that shallow depression. Physicists are careful about the language they use here. The timescales involved in any tunneling event, if the metastable picture is correct, are likely to vastly exceed the current age of the universe by many orders of magnitude. And the measurement uncertainties in the Higgs mass and in the closely related mass of the top quark mean that the picture could still shift toward full stability when better measurements arrive. The precise location of the universe on the stability map is not yet determined. But the principle is the thing. The particle physicists spent nearly 50 years hunting turned out to carry a mass that plays.
There is a story spreading across the internet right now, and it is the wrong story. It involves secret alarms, hidden control rooms, and the breathless claim that physicists buried deep beneath the Franco-Swiss border have accidentally punched a hole through the fabric of space-time. Forums are filled with it. Comment sections are drowning in it. And I want to address it directly, because the real story, the one that is actually unfolding in the data, in the collision statistics, in the quiet and increasingly urgent conversations between theoretical physicists across the world is so much more profound, so much more unsettling, and so much more beautiful than any science fiction scenario the internet has conjured. Nobody at CERN has created a black hole. Nobody has opened a portal to a parallel dimension in the cinematic sense. The Large Hadron Collider is not a doomsday machine. But here is what is genuinely, deeply, mathematically alarming. The equations are starting to fail, not catastrophically, not in a way that makes headlines the way an explosion would, but in a way that every serious physicist recognizes as the most dangerous kind of failure there is, a quiet, systematic, statistically significant divergence between what our finest theoretical framework predicts and what the detectors are actually measuring. That is the panic. It is not the panic of an accident. It is the panic of comprehension, the dawning realization that the foundational architecture of particle physics, the model that has guided our understanding of matter and energy for half a century, is cracking at its mathematical foundations. To understand why this is so significant, I want you to imagine something. Picture all of human civilization living its entire existence on the surface of an enormous drum. Not inside the drum, not beneath it, but precisely on that thin, taut membrane stretched across its top. Generations are born on this surface, cities are built on it. Every telescope ever constructed points outward across it. Every particle accelerator ever designed fires beams along it. And over centuries, humanity constructs an extraordinarily beautiful, comprehensive theory of everything that exists on this surface. The mathematics is airtight. The predictions are astonishing in their accuracy. Physicists stand at the edge of this drum skin and declare, with complete mathematical justification, that this surface is the totality of physical reality. Now imagine that a civilization, through extraordinary engineering, constructs an unimaginably powerful hammer. And they bring that hammer down onto the surface of the drum with a force equivalent to recreating the energy conditions that existed a fraction of a second after the universe began. And the drum does not simply vibrate the way their equations predicted. Instead, they hear something impossible. They hear resonances echoing from beneath, from a direction their physics has no coordinate for. From a spatial architecture, their equations contain no variable to describe. The drum skin, they begin to realize, is not reality. It is a membrane, impossibly thin and impossibly fragile, stretched across the outer face of an architecture so vast and so complex that the surface dwellers have never possessed the sensory apparatus to perceive it. That is not a metaphor I am using loosely. That is, in a genuinely precise technical sense, what the data anomalies emerging from high-energy proton collisions at CERN are beginning to suggest. And the theoretical implications reach into three distinct areas of physics, each one more disorienting than the last. The first is what I would call the arrogance of visible matter. For most of human history, and indeed for most of the history of modern physics, we have operated under a deeply intuitive but profoundly incorrect assumption. We have assumed that the stuff we can see, the protons and electrons and photons that compose every atom of every star and every human body and every instrument we have ever built, constitutes the physical substance of the universe. We assumed this because it was the only thing our instruments could detect. And our instruments were, for a very long time, extraordinarily good at confirming our assumptions. But the numbers do not lie, and the numbers are brutal in their honesty. The matter that emits or interacts with light, what astronomers call baryonic matter, constitutes approximately 5% of the total energy content of the observable universe. 5%. Everything you have ever seen, every galaxy imaged by every telescope ever launched, every particle ever fired through every accelerator, every atom in every human body on this planet, accounts for 5% of what is physically out there. The remaining 95% is something else entirely, something our standard model, our most precise and comprehensive theory of particle physics, does not describe, does not predict, and in its current mathematical form, cannot accommodate. This would be uncomfortable enough as an astronomical observation, but now the discomfort is arriving at the subatomic level, which is a different order of crisis entirely. When protons are accelerated to energies approaching the theoretical predictions of the Standard Model and then collided inside detectors the size of cathedrals, the resulting debris field should be fully accounted for. Every quark fragment, every lepton spray, every photon, and every unit of energy should appear somewhere in the detector readout. The mathematics of conservation is ironclad. Energy does not vanish. It transforms, it disperses, it radiates in measurable directions, except that in certain collision events at specific energy thresholds, the accounting does not close. There are statistical signatures in the data that suggest energy is going somewhere the detectors cannot see, somewhere that is not simply off to the side or absorbed in shielding material, but somewhere that is orthogonal to every spatial direction the detector possesses. The second area of profound theoretical consequence is the architecture of extra dimensions. This is where string theory and the family of models it has inspired become not merely an abstract mathematical indulgence, but a concrete, testable framework for understanding what the collision data might be telling us. The central insight of string theory is that the fundamental constituents of matter are not point-like particles, but one-dimensional filaments of energy, strings vibrating at specific frequencies in a space that contains not 3, but 10 or 11 spatial dimensions. The reason we perceive only 3 spatial dimensions, according to these models, is that the remaining 6 or 7 are compactified, curled into microscopic geometric structures at scales so small that our best instruments have never been sensitive enough to resolve them. These extra dimensions are not in some distant region of space, they are here. They are woven through every cubic centimeter of the space you currently occupy. They are present in the room around you right now. They are folded into the geometry of space-time at scales billions of times smaller than a proton. And the reason we cannot perceive them is not because they are mysterious or metaphysical, but simply because our sensory apparatus and the instruments we have built as extensions of that apparatus do not operate at the energy scales required to probe those geometric structures. The brain world models, which are a class of theoretical frameworks derived from string theory, add an additional layer of precision to this picture. In these models, our observable universe is not the full extent of space-time, but rather a 3-dimensional surface, a brain, embedded within a higher dimensional bulk. Matter and the electromagnetic force, the light and particles we are made of and detect with, are confined to this brain. We are, in a mathematically rigorous sense, surface dwellers. We cannot escape the brain using any conventional physical interaction because those interactions are themselves brain-bound. But gravity, alone among the fundamental forces, is not confined to the brain. Gravity propagates into the bulk. And this is not a speculative poetic flourish. This is a specific, testable mathematical prediction. If these models are correct, then high-energy collisions that produce sufficiently small structures at scales approaching the compactification radius of the extra dimensions should produce gravitational radiation that leaks into the bulk. The energy carried away by this bulk-bound gravitational radiation would appear in our detectors precisely as missing energy, as a systematic shortfall in the collision accounting that grows more pronounced at higher energies and at specific angular distributions that carry the geometric fingerprint of the extra-dimensional structure. The anomalies being detected at CERN are not yet at the level of a definitive confirmation, but they are at the level where the theoretical physicists who understand these models best are no longer dismissing the possibility, and that change in posture is significant. The third area of consequence is what I think of as the phantom physics of the dark sector, and this is where the intellectual vertigo becomes genuinely difficult to manage. Dark matter is not simply invisible matter of the kind we are already familiar with, ordinary atomic matter that happens not to emit light. The astronomical and cosmological evidence constrains its properties with extraordinary precision, and those constraints rule out every known particle in the Standard Model. Dark matter must be composed of something for which we currently have no description whatsoever. It interacts gravitationally, which we can measure through its effect on galactic rotation curves and gravitational lensing. Beyond that, its interaction cross-sections with ordinary matter are so suppressed that decades of extraordinarily sensitive direct detection experiments have produced no confirmed signal. Dark energy is an even deeper crisis. It constitutes approximately 68% of the total energy content of the universe. It is causing the expansion of space itself to accelerate, and our best theoretical calculation of what it ought to be, derived from quantum field theory, is wrong by a factor of 10 raised to the power of 120. That is not a rounding error. That is the largest quantitative discrepancy between theory and observation in the entire history of science. But the aspect of the dark sector that is generating the quietest and most sustained alarm is the emerging possibility that dark matter and dark energy are not passive features of the cosmic background, not simply a gravitational scaffolding and an energy reservoir, but active components of a parallel physical framework governed by dark forces, mediated by dark particles, operating according to interaction laws that are entirely separate from the four fundamental forces we have mapped. There could be a dark electromagnetism, there could be dark nuclear processes, there could be a physics of extraordinary complexity and richness unfolding in the dark sector, superimposed directly over every region of space we have ever observed, utterly invisible to us, not because it is in some remote location, but because we do not possess the physical receptors to interface with it. The detectors at CERN were not designed to see this dark sector directly, but they were designed with extraordinary sensitivity to the bookkeeping of energy and momentum. And it is precisely that bookkeeping in those specific high-energy collision regimes where the numbers are beginning to suggest that the boundary between the visible and the invisible is not as impermeable as our equations have assumed. And this is the genuine story, not a disaster, not a doomsday, but something far more confronting than either of those things. The confrontation with the boundaries of human perception, formalized in the language of mathematics, made concrete in the statistics of subatomic debris fields, is not the end of physics. It is something rarer and more precious than that. It is physics arriving at its own edge and discovering, with instruments precise enough to register the fact that the edge is not a wall, but a threshold. Human biology evolved to navigate a thin sliver of physical reality. Our eyes detect a narrow band of the electromagnetic spectrum. Our fingertips resolve features down to roughly 1/10 of a millimeter. Our nervous systems process information at frequencies relevant to the timescales of biological survival. None of these capacities were shaped by evolutionary pressure to perceive compactified extra dimensions or dark sector force mediators. We are, in the most literal physical sense, being There is a story spreading across the internet right now, and it is the wrong story. It involves secret alarms, hidden control